Today we are going to correct our Christmas worksheet. Now let's start with exercise number 1. Copper with the chemical symbol Cu and zinc Zn form an alloy called brass of mass 80 gram. The chemical analysis of this alloy shows that it contains 20% by mass of copper. Given the molar masses for copper 64 gram per mole and for zinc 65 gram per mole, in addition to the Avogadro's number. Question number 1. Determine the mass of copper in the alloy. We are going to use this formula where the percentage by mass of copper it's equal to the mass for copper divided by the total mass for the alloy, which is equal to 80 gram times 100, since it is a percentage. So here we can deduce that to calculate here the mass for copper, it's equal to the percentage by mass times the total mass of the alloy divided by 100. So you will find that the mass of copper in this alloy it's equal to 16 gram. Question number 2. Deduce the mass of zinc in the alloy. The total mass of the alloy it's equal to the mass of copper in addition to the mass of zinc. It's equal to 80 gram, which is given for you. So here we can deduce that the mass for zinc is equal to the total mass of the alloy minus the mass for copper. So it's equal to 80 gram minus 16 gram, it's equal to 64 gram. Now moving to question number 3, calculate the number of moles of each metal in the alloy. So we are going to calculate small letter n, the number of moles for zinc and for copper. So you will use this formula, the only one, number of mole it's equal to the mass over the molar mass. Let's start to calculate the number of mole for zinc. So it's equal to 64 gram, which is the mass for zinc, divided by its molar mass, which is given for you, 65 gram per mole. So the number of mole for zinc it's equal to 0.98 mole. Now for copper, we will use the same formula. The number of mole for copper it's equal to 16 gram divided by the molar mass, which is 64 gram per mole. So you will find that the number of mole for copper it's equal to 0.25 mole. Now moving to question number 4, calculate the number of zinc atoms in the alloy. So you have to find capital letter N, which represent the number of zinc atoms, and you have the Avogadro's number. So here number of mole for zinc it's equal to the number of atoms divided by the constant Avogadro's number. So you will find that the number of zinc atoms it's equal to the number of mole times the Avogadro's number, and it will be equal to 5.8996 times 10 to the power 23 atoms. Now moving to the second exercise, a rock sample contains the following metals: 10.80 gram of copper, 0.2 times the Avogadro's number, atoms of aluminum, and 0.5 mole of iron. Given for you respectively the molar masses in gram per mole for copper 64, for aluminum 27, for iron 56, and you have the Avogadro's number. Question 1. Determine the mass of iron and aluminum in the rock sample. So here you need to find the small letter m, the mass for iron and for aluminum. So let's start calculating the mass of iron. The only information you have the number of mole for iron, n equals 0.5 mole. So we can say that n equal mass over molar mass, and directly you can calculate the mass for iron, which is equal to the number of mole times the molar mass, and you will find that the mass for iron it's equal to 28 gram. Now for aluminum, the only information is that the number of aluminum atoms it's equal to 0.2 times the Avogadro's number, and it would be equal to 1.204 times 10 to the power 23 atoms. So here I'm gonna use the relation mass over molar mass. It's equal to the number of aluminum atoms divided by the Avogadro's number. And you have the molar mass for aluminum, it's equal to 27 gram per mole. So just substitute the given information and you will find that the mass for aluminum, it's equal exactly to 5.4 gram. Now question number 2, deduce the mass of the rock sample. According to the text, a rock sample contains the following metals. We have copper, 10.80 grams, so you have already the mass for copper. You have 0.2 Na atoms of aluminum and 0.5 mole for iron. Now you can say that the total mass of the rock sample is equal to the mass for copper plus mass of aluminum plus the mass for iron. Mass for aluminum, it is already calculated, it's equal to 5.4 gram. Mass for iron is equal to 28 gram. So you have just to add 10.80 gram from copper plus 5.4 gram, which is the mass for aluminum, plus 28 gram, which is the mass for iron, and you can find that the total mass of the rock sample is equal to 44.2 gram. Now question number 3, calculate the percentage by mass of copper in the above sample. I'm gonna use the same formula, percentage by mass for copper, it's equal to the mass of copper divided by the total mass for the rock sample times 100. So it's equal to 10.80 gram, which represents the mass for copper, divided by the total mass for the rock sample, 44.2 gram, times 100, and you will deduce that the percentage by mass of copper in this alloy, it's equal to 24.43%. Now moving to exercise 3, the percentage of abundance of different atoms of lead is shown in the table below. Question number 1, the above atoms are isotopes, justify. The above atoms are isotopes since they have the same atomic number but different mass number and different number of neutrons. Question number 2, determine the percentage abundance for lead 208 and lead with the mass number 204. So here, looking at this table, to calculate the percentage abundance for both of them, you need first to calculate X. So how to calculate the small letter X? Here you can add all the percentage relative abundance and they will be equal to 100. So we can say that 1.37, which is the percentage abundance for the first isotope with the mass number 207, plus X plus 5.46 plus the percentage abundance for the last one, 51.5. All of them, they are equal to 100 since they are a percentage. So here, by calculating X, you will find that X equal 20.84%. Then the percentage abundance for lead 208, it's equal to X, 20.84%, while the percentage abundance for lead 204, it's equal to X plus 5.46, so it's equal to 26.3%. Now question number 3, show that the average atomic mass of lead is 206 U. Now you will apply this formula where the average atomic mass, capital letter M, it's equal to the mass number for the first isotope, which is equal to 207, times its percentage abundance, which is equal 1.37, plus the mass number for the second isotope, 208, times its relative abundance, plus the mass number for the third isotope times the relative abundance, plus the mass number for the last isotope, A4, which is equal to 206, times its relative abundance, all of them divided by 100. So it will be equal to 205.9 AMU. So it's approximately 206 U. Now moving to to exercise 4, given the following set of elements. Question number 1, if 43.2 gram of germanium contains 35.5 times 10 to the power 22 atoms, determine the molar mass of germanium. So you have to find capital letter M, the molar mass for this element. So here we have small letter m, the mass 43.2 gram, and you have the capital N, the number of atoms. So I'm gonna use again the relation. So we can write here that the molar mass for germanium is equal to its mass times Avogadro's number divided by capital letter N, which is the number of germanium atoms. So we can say here, by substituting all the given information, we can say that the molar mass for Ge is equal to 73.2 gram per mole. Now question number 2, bromine occurs in nature as a mixture of two atoms, Br79 and Br81. The average atomic mass of bromine is 79.98 AMU. Part A, justify what do we call the above atoms. Looking at the atomic symbol for each one, we can say that they are isotopes because they are atoms of the same element, bromine, that have the same atomic number, 35, but different mass number, 79 and 81. Now part B, determine the percentage abundance of each atom. Here you have the average atomic mass for bromine, and here we can say that let the percentage abundance for the first isotope equal to X and the percentage abundance for the second isotope equal to 100 minus X. So we can say that the average atomic mass is equal to the mass number A1, which is 79, times X, which is the relative abundance for the first isotope Br79, plus mass number of the second one, 81, times the percentage relative abundance, which is equal 100 minus X over 100. So here you can find that X, it will be equal to 51. So we can deduce that the percentage relative abundance for Br79 is equal to X, is equal to 51%, while the percentage relative abundance for the second isotope, it's equal to 100 minus X, it's equal to 49%. Now question number 3, arsenic atom As has a mass of 1.2525 times 10 to the power minus 25 kilogram. The boiling point of arsenic is 603 degrees Celsius. Part A, determine the atomic number of arsenic if the atomic number capital letter Z equal A minus 42. So here, in order to calculate the atomic number, first of all you have to find the mass number capital letter A. So looking at the given information, you have only the total mass of the atom, which is equal to 1.2525 times 10 to the power minus 25 kilogram, and we can say that the total mass of the atom is equal to the total number of its nucleons times the mass of each nucleon, which is given for you. The total number of nucleons represent the mass number, which is A, which is the total number of protons and neutrons. So here we can say that mass number A, it's equal to the total mass of the atom, which is given for you, divided by the mass of each nucleon. You will find that the mass number equal to 75, and we can say now that the atomic number equal to 75 minus 42, using the relation the atomic number it's equal to 33. Now moving to exercise 5, we have the atomic number for magnesium, it's equal to 12, given the elementary charge, and you have the Avogadro's number. Question number 1, write the electron configuration of magnesium atom. So here, using the diagonal rule, you can say that since atom is electrically neutral, number of protons equal to the number of electrons equal to the atomic number equal to 12. So we can say that electron configuration of magnesium atom, it's 1s2, 2s2, 2p6, and 3s2. Now moving to question number 2, identify the location of magnesium atom, the column and the row. Looking at the electron configuration for magnesium, we can say that magnesium atom belongs to column 2. So my justification will be, since all elements that belongs to column 2 end with s2, so we can say also that magnesium atom belongs to row 3, since row is the number preceding the last s shown in the electron configuration. Now moving to question number 3, determine the valence electrons and then write the lowest dot symbol for magnesium atom. Here, valence electron is equal to just 2 electrons. If the electron configuration here ends with s2, we can deduce directly that the valence electron is equal to 2. Now for the lowest dot symbol for magnesium, it is the chemical symbol, which is Mg, surrounded by 2 dots which represent the valence electron. Now question number 4, determine the atomic number of the element just after magnesium in the periodic table. Looking at the periodic table, you can say that elements are arranged according to their increasing order of their atomic number, Z. So here, given for you that the atomic number for magnesium is a 12, so we can say that the atomic number of the element just after magnesium in the periodic table, it's equal to 13. Now moving to number 5, calculate the mass number of magnesium if the number of neutrons is equal to 12. So to calculate the mass number, I'm going to use the relation, the only relation, A equals Z plus N. So it's equal to the atomic number 12 plus the number of neutrons, which is given for you, also 12. So the mass number equal to 24. Now question number 6, deduce the molar mass for magnesium. The molar mass for each element, it's equal to the mass number, and you write adjacent to it the unit, which is gram per mole. So the molar mass for magnesium, it will be 24 gram per mole. Question number 7, calculate the nuclear charge of magnesium. The nuclear charge for magnesium is equal to the atomic number times the elementary charge of each proton. So it's equal to 12 times the elementary charge, which is given for you, is equal to plus 1.6 times 10 to the power minus 19 coulomb. So we can deduce here that the nuclear charge of magnesium is equal to plus 1.92 times 10 to the power minus 19 coulomb. Now question number 8. A bar of a chocolate has 48 milligrams of magnesium. Determine the number of moles of magnesium present in the chocolate bar. First of all, you have to convert from milligram to gram, since for the mass, the used unit in chemistry is gram, not milligram. So here we can say that the mass for magnesium equals 48 milligram divided by 100. So it's equal to 0.048 gram. Now you need to calculate small letter n, the number of moles for magnesium. So it's equal to mass over molar mass. So it's equal to 0.048 gram divided by molar mass 24 gram per mole. And it will be equal to 2 times 10 to the power minus 3 mole. So this is the number of mole for magnesium. Now part 8.2, deduce the number of atoms of magnesium present in the chocolate bar. So we need to calculate capital letter N. So I'm gonna use this relation and equal the number of atoms divided by the Avogadro's number. So we can say that capital letter N, which represent the number of atoms for magnesium, it's equal to 1.2 times 10 to the power 21 atoms. Now moving to exercise number 6. The molecular formula of glucose is C6H12O6. Given the molar masses in gram per mole respectively for carbon 12, for hydrogen 1, and for oxygen 16, and you have the Avogadro's number. Question number 1. Find the atomicity of a glucose molecule. Atomicity represents the total number of atoms. So here we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So the atomicity for a glucose is 6 plus 12 plus 6, so it's equal to 24 atoms. Question number 2. Specify whether glucose is a polyatomic or a diatomic molecule. So here glucose is a polyatomic molecule since it is made up of more than 2 atoms. We have 24 atoms. Question number 3. Calculate the molar mass of a glucose. So here the molar mass for a glucose, it's equal to respectively, let's start with carbon. We have 6 carbon atoms, so 6 times the molar mass for carbon, which is 12, plus 12 times the molar mass for hydrogen, plus 6 times the molar mass for oxygen, and it will be equal to 180 gram per mole. Now question number 4. Determine the number of molecules, capital letter N, of a glucose that corresponds to 0.5 mole of a glucose, and you have a small letter N, the number of mole. So here I'm gonna use this formula, N equal capital letter N, which represents the number of molecules divided by the Avogadro's number. So the number of molecules always is equal to the number of moles times the Avogadro's number, and you will find that the number of molecules is equal to 3 times 10 to the power 23 molecules. Now question 4.2. Determine the mass of 1.5 times 10 to the power 24 molecules of a glucose. So I need to calculate small letter m, and you have capital letter N, which is the number of molecules. So here I'm gonna use the relation directly, where the mass of a glucose over the molar mass, it's equal to the number of molecules, which is given, over the Avogadro's number. So you need to calculate small letter m mass, so it's equal to the molar mass times the number of molecules divided by the Avogadro's number. So directly we can deduce that the mass of a glucose, it's equal to 5.4 gram. Now question 4.3. The number of moles that corresponds to 1.8 times 10 to the power 22 molecules of a glucose. I need to calculate the number of moles, small letter N, and you have the number of molecules. So here directly I'm gonna use this relation, number of moles equal to the number of molecules, capital letter N, divided by the Avogadro's number. So by substituting the given information, you can say that the number of moles for glucose, it's equal to 0.03 mole. Please be safe and keep up the good work. Thanks for watching.